Hello, hello. We would like to welcome you back to PSSB, Physical Sciences, Silver Bullet, and the name behind the channel is Richard. We would urge you to subscribe. It's very important that you do so that you don't miss a series of number of videos we are going to be posting. Like we said, all the topics, all the areas are going to be discussed here using the skills I have attained over a number of years. So we would urge you to sit back, relax, call others, spread the gospel. Yeah. Now we are having the same setup as before. And the question is here. The question says, calculate the standard reduction potential of the cell above and identify the metal A. So we go back to what we did before, what we know. We say that the standard cell potential of the cell is given by E naught, or standard reduction potential of cathode, minus E naught anode, or standard reduction potential of anode. Now, when you look at the cell, we already identified anode and cathode. How did we identify them? By virtue of the signs. The signs were given to you, the plus and minus. And we said, which we are still emphasizing because of its importance, that there is this is a bit contrary to what we know in electrolytic. For galvanic, the positive is cathode and the negative is anode. So with that information, now we know what is cathode here. Our cathode is the AA, which we don't know. So, but we know the cell potential, which is 0.8. So a cathode is X minus E anode. Now, you have to remember that hydrogen is used as a reference electrode. It is the electrode upon which all other electrode potentials were measured, and it is given number 0.0. So it has 0.00 voltage. So with this in place, we can proceed and compute our X, the unknown, the A. So it is apparent here that 0.80 volts is what X is. Or we can put it better, that X has a standard reduction potential of 0.80. Then after this, there is a part here on the question which says identify metal A. How do we identify metal A? We go to the table of standard reduction potentials and we look for the metal which is having this value. When you go there, that metal is found to be silver. Silver has standard reduction potential of 0.8, positive 0.8. So now we've already identified it. So therefore, the metal A is Ag, or silver. Okay, that question's been answered. Then comes this question 2.6. It says that 100 cubic centimeter of 1 mole per cubic decimeter of solution of A ions is added to the half cell of A. State what happens to the cell potential of the cell. Now, to answer this question, there's some information we need to know. I want us to look at this. It's very important that we take note of that. That is 1 mole per cubic decimeter. And I want also to recall what we said about the standard conditions of this cell. One of the conditions was that the concentration of these half cells have to be 1 mole per cubic decimeter. What is the implication of that? The implication is very simple, that you are adding the same concentration to this half cell, the concentration which it has. Now, the question would be, what are you doing to the concentration? Obviously, you're not changing anything. The concentration remains 1 mole per cubic decimeter. The only thing you are changing is volume. And we don't have anywhere where volume is having an effect on the cell potential. So with that background, what is the answer to this question? The answer is no change. In bracket, cell potential remains the same. So that is that. Then comes this question. Let us analyze it. We are saying that hydrogen half cell, which is this half cell here, is now replaced by this half cell, the X half cell. So in other words, we are taking out hydrogen and you're replacing it with X. So our setup now is having A here and X there. Then they give you the cell notation of the cell. And this is also a very important information for this question. They give you that cell notation and they say the initial voltmeter reading is this one. They say identify metal X. Okay, how do you tackle this question? This is the information we have so far, which we can get. One is that we know the cell. Let me use another color. We know the cell potential. It has been given. And it is 1.56 volts. What else do we know? We are given this this cell notation, but you have to remember that for cell notation you have to get this information. What you start with here is A. because you know in the cell notation A is on the left. And what we have here is C. But you have to remember that we found already A in our previous video. We found that the standard reduction potential of A was 0.8 volts. So that information is very crucial because we are going to need it. So what do? We bring in our equation. The equation says that E naught cell is equal to E naught cathode minus E naught anode. So, but E naught cell is known and is 1.56. E naught cathode, we know it, and it is 0.80. What we don't know is our X. Our X is the anode, so we don't know it. So let us call it X in that aspect. So when you rearrange this equation, what are we going to have? You are going to have X being equal to 0.80 minus 1.56. And after computation, what do we get? You get minus 0.76 volts. That's what you get. Now, what you have here is the standard reduction potential of X. And now comes the next part of identifying it. How do you identify it? You go to the table of standard reduction potential to find out which element is having this value. So the element is zinc. So zinc is X, or X is zinc, and that is it. That's how we answer that question. There comes this question 2.7.1. It says, give a reason why the calculated cell potential might differ from that measured. So at times you might set up a galvanic cell and you have your electrolyte, your electrode, and the voltmeter. And when you take the voltmeter reading, the value is different from that one which you have in that one which you calculate using the standard reduction potentials. So that's what this question is addressing. The question says, what might be the cause of that? What might be the cause of the difference in the expected reading to what you actually read from the voltmeter? Now, this question is answered by looking at the deviations from the standard conditions. It's the deviation which causes the difference in the readings we obtain. What are the deviations? Okay, you have to go and look at the standard conditions. First one, the environmental temperature. might not be 25 degrees Celsius. Okay, then what else can cause the deviation? The other one is the concentration of the electrolyte might not be 1 mole per cubic decimeter. The third one is that the pressure of the gas involved, in case one of the half cell has gas, the pressure of the gas might not be 101.3 kilopascals or 1 atmosphere. So these three factors can seriously influence the value you obtain, you read from your voltmeter. Then lastly, about the setup, this question comes. The question says that in the setup above between hydrogen half cell, this one, and A half cell, this one, the half cell of A, this cell, is replaced by X, the one we just calculated. And the question comes, it says, what will be the voltmeter reading this time at standard conditions? I want you to remember what we are doing. What are we doing? We are maintaining the hydrogen half cell, and we are taking away the A half cell, and we are replacing it with the X half cell. So the setup is between hydrogen half cell and A and X half cell. A is gone. So instead of A, we have X. What would be the reading? Now, I want to remind you that hydrogen has standard reduction potential 0. So any element you connect with the hydrogen, the cell potential here is supposed to be the standard reduction potential of this element. You see, this was zinc. Sorry, this was silver. And what is the standard reduction potential of silver? 0.8. So if you put copper here, let me recall, what is the standard reduction potential of copper? It is 0.34. This one will read 0.34. And you have to remember that because this cell is spontaneous, the reading here is always positive. So what is going to be the reading when you connect our X? We found our X to be zinc. And the standard reduction potential of zinc is 0.76. So what is going to be the reading at the voltmeter? The reading is going to be 0.76 volts. Don't forget and put on the negative. The negative is sorted out by the change of the terminals, but the reading here, I have to remind you, it is always positive. Why? Because galvanic cells are spontaneous. Thank you. Don't forget to subscribe to PSSB, Physical Sciences Silver Bullet. Thank you.